Hello everybody and welcome to NPTEL online certification course on cryogenic electronics for quantum computing. This is lecture number 33. The topic of this lecture is change in threshold voltage, a trap based analysis, a trap charge based analysis. So we will start from where we left in the previous lecture, that if you remember, there are two types of trap charges which are there. One is the oxide trap charge, which is primarily the charge which is located within the silicon dioxide layer, right? And these oxide trap charges remain some few angstrom away from the silicon dioxide interface, and they are sort of trapped in that particular domain for a substantially long amount of time. They also influence the threshold voltage, but there is another trap charge which is known as the interface trap charges, which lie exactly at the silicon dioxide interface, primarily because of two reasons. One is because of the bonds are not properly satisfied, and therefore there are some hanging bonds available which acts as a trap for the charge carriers. The other is basically that if the oxidation is not proper in the silicon dioxide region, there are also interface trap charges which are available, and these trap charges primarily are regions of low energy, and therefore any charge particle or particle will actually get trapped in that and remain there for substantially long amount of time, right? Thereby changing the carrier concentration. There is also a detrapping of charges which happens when the temperature goes high. The charge particles are removed from the trap charges and they enter into the stream. But we will not go into details of detrapping now. What we are concentrated is how it changes the threshold voltage at cryogenic temperature. So typically the traps are modeled in a Gaussian fashion, right? What do I mean by that? I mean to say that if you look at the right hand side figure here, or this one, then you will see that most of the traps is around the conduction band edge. You see the most of the charges are here, and the maximum value is n naught upon sigma times root 2 pi, where n naught is the maximum number of charges, sigma is full width at half maxima, into square root of 2 pi is there. This is the maximum value of charges which is there, and they are close to the band edge, right? This is very close to the band edge. This is my EC band edge and this is very close to it. W0 is my width, right? A 3 sigma width, basically telling me that most of the interface trap charges are all located within this W0 plane only. So around plus minus 10 milli electron volt around the conduction band edge. So if you have an edge here, right, then they are concentrated somewhere in this edge, right? Most of the charge particles are concentrated. If you go beyond this, there is an exponential decay in the number of interface trap charges. For an N-type MOSFET, only negatively charged acceptor traps in the top half of the band gap. So if you remember, when you have this conduction band, valence band, you have this intrinsic EI at the middle. So all the negative charge acceptor ions in the top half of the band gap are significant, right, for the interface trap charges. The value of interface trap charges is approximately given as minus q times du multiplied by psi s minus phi f star. Psi s is the surface potential and phi f star is primarily the modified Fermi potential because of interface trap charges. Du is a constant which is typically of the order of 10 to the power 10 centimeter per centimeter square per electron volt for all practical purposes. We also assume that the Fermi function is basically a step function. When we were discussing the Fermi potential, we said that probability is 1 above Fermi and it is 0. So we define this to be as a step function. So this is defined as a step function. At uniform occupancy is maintained. So we are assuming that beyond the Fermi potential, uniform occupancy is maintained across the band gap. So the interface trap charges gives me this value. W0 is width and it is approximately equals to 2 sigma. So this is basically your 1 sigma here, full width at half maxima, and this is your another sigma coming from here. So these 2 sigma, when you add up, I get W0 equals to 2 sigma as the value which you get. Now the density, this du value, the density of the dangling bonds which I had told you earlier, this constant value, this du here, this does not changes significantly when you go down to the cryogenic temperature, and the reason is the dangling bonds are primarily by virtue of fabrication, right. So when you actually fabricate and you try to do, let us suppose you are doing a wet oxidation or otherwise, the density of the dangling bond actually does not change too much while you are going down to the cryogenic temperature around 10 Kelvin or so. Now, if you look at the charge, how you define the total charge because of the interface trap charges is given by this expression which is shown here, right. It Q0 equals to minus Q times integral of d0 dE, which we integrate from intrinsic Fermi level to the Fermi level which we see, right. And this d0 E is considered to be Gaussian in nature, right. So, there will be a fixed term and there will be an exponential term. The fixed term can be brought outside the integral and the variable term can be integrated in a sense. Now, typically this integral does not have an analytical solution. There is a numerical solution of course, but there are no analytical solutions because of non-integrability of the system, right. Now, we are assuming that the Gaussian traps are spread uniformly across the network, right, and gives me a fixed value. Now, to simplify, we will not go into how you are finding it out, but finally we get the value of Q0 to be this much. This is the charge contribution because of the interface trap charges in the system, where W0 is always the width at half maxima. So, if you look at this Gaussian surface, this is at half maxima, this is maxima, right. The half of maxima is this one, this is half the maxima, right, and therefore, we define the width there as W0. So, W0 by 2 into root 2 error function plus 1 into Q into N naught by 2, where N naught is the maximum, basically the maximum number of trap charges at the center when the at EC, right, the maximum Gaussian surface which you see. And EC is the conduction band edge, EF is the Fermi level which you see. And quite interestingly, and I leave as an exercise to you, you can think about it yourself. So, just go back to a error function and check what happens to what is the value of error function at 0, right. Why? Because if you look at this numerator of this within the parenthesis, when EF becomes almost equals to EC, that is the point where you actually have this going to 0, error function goes to 0. So, check out what will be the value of Q0 at that particular point, right. There might be also a case when degenerate semiconductor takes place that your EF goes well within the conduction band edge and there might be a negative value of EC available to you. Let us look at therefore the modified sort of threshold voltage model at cryogenic temperature. As I discussed with you earlier, the threshold voltage will depend therefore on the modified surface potential psi A star. It will depend upon the work function difference, it will depend upon the body effect, and it will also depend upon the contribution of uniform and Gaussian interface trap charges. So, there are two trap charges which are available. One is a uniform trap charge, right, and one is a Gaussian interface trap charges. Uniform trap charges are fixed per unit area, per unit volume, and they do not vary with space, whereas Gaussian trap charges will vary with energy as well, as I have shown you earlier. So, the uniform trap charges is given by this formula and the Gaussian trap contribution is given by this formula, right. The first one depends upon du, the second one depends upon N naught, and these are the functions which are available in this case. The modified surface potential is given as the sum of the modified Fermi potential, which is this part, right, and Eg by 2. Eg by 2, why you divide it by Q to get into potential. So, Eg by 2 because you are in the band gap, center of the band gap. So, this was your Eg, right, and this is your Eg by 2, the center of the band gap which you see, right. So, what you need to do is that you need to substitute the value of psi A star from here, you need to substitute the value of phi ms here, get the value of phi f star and insert it into the threshold voltage model, and that is what we have done exactly here. So, therefore, this equation of threshold voltage consists of modified surface potential, the work function difference between metal and semiconductor, body effect sort of account, and you also have two parts, one is the fixed charge and another is the Gaussian. So, this is your Gaussian traps and this is your fixed traps. So, we already have phi ms equals to phi m minus phi s, which is equals to phi m minus chi. This phi m minus phi s will be, this phi s can be actually again broken down as I discussed with you earlier into electron affinity minus chi minus phi f star minus Eg by 2. So, if you look at this expression here, which is threshold voltage expression in the first place here, then it consists of two parts, and that two part is psi S star and psi S star and psi S prime and psi S star. Psi S star comes from the fact, let's go back here. Let's yes, so this is EF and EC. So this corresponds to EF and this corresponds to EC, and W0 is the width at half maxima which you are trying to find out, right? Now you will see very interestingly that the threshold voltage is in a sense inversely proportional to the value of Cox, which means that if Cox actually starts to go down, right, it starts to decrease, then I will have my threshold voltage increase taking place here, right? And if Cox value goes up, the threshold voltage value goes down. Now, if you remember Cox, oxide capacitance per unit area, let me say, then it's epsilon ox by Tox. Tox is the thickness of the oxide layer. So, if you make a thickness of the oxide layer go high, right, Cox goes low and Vt goes high. And that is true also, because as you make your oxide thickness larger, you end up having a lesser control of the gate over the channel, and that is the reason the threshold voltage will rise up. Let us look at the second part here, that is psi S star. Psi S star is the modified surface potential in place of cryogenics, and it depends primarily linearly on the value of psi S star in one case and parabolically in other case. So, square root here psi S to the power 1 by 2, which you find out for the threshold voltage in this case. So, if you look carefully, when you start finding out simulating the value of threshold voltage, most of the quantity here, right, are constant except psi S prime is not constant. Similarly, given everything else, here everything is constant, here also everything is constant, again psi S star is not constant, and psi S star will change depending upon the bias which you put, right, which bias? The gate bias. And therefore, threshold voltage beyond a point is also a function of the gate bias at a certain point of time. It not only depends upon temperature, because as you vary the temperature, this psi S star also tends to vary, and therefore threshold vary. So, numerically we have seen two things, that threshold voltage is a strong function of temperature even at cryogenic temperature, but not only that, it also depends upon many factors such as uniform traps and Gaussian traps. Now, if you find out the value of psi S star, it is given as 2 phi f minus del phi f, where del phi f is the difference in the phi f between Na and the modified. So, this del phi f which you see here, this is del phi f here, and we do is 2 phi f minus del phi f we do. This del phi f, if you remember, is the difference between EF and EF star, right, if you remember our previous band diagram here. So, this EF minus EF star is primarily because of the difference in the Fermi level when you do a generate and degenerate semiconductor. I get 2 phi f minus del phi as equals to psi S star. Now, if you put the value of this psi S star, which you have just now derived, this one, and phi ms into Vt, I get this expression here, right. So, this is the final expression which we get for Vt. So, this psi S star is being replaced by 2 phi f minus del phi f, and this is phi f minus del phi f. So, that is the reason we get this overall expression as q times du times phi f by Cox as 1 point, then q n naught by 2 Cox upon error function of this value here, and so on and so forth. Now, not only that, as I discussed with you, your band gap will be also a function of your temperature. As you change the temperature, the band gap also changes, and that influences also your threshold voltage at low temperature. So, this is the final expression which you see at the top. Now, if there are no traps, what I need to do is if I am assuming that you do not have any traps and it is perfectly normal semiconductor or perfectly ideal semiconductor, then we can simply replace du to be equals to 0, which means that this goes to 0, right. If I assume there are no Gaussian traps, this goes to 0. So, if there are no traps, these two terms vanish, and we are only left with the first three terms, which are again temperature dependent. Now, if there is a bulk, this is known as the bulk dopant freeze out, which we have already discussed, right. In case that there are no freeze outs, does not happen at cryogenic, at room Kelvin, del phi f will be almost equals to 0. Now, but even if I insert the quantitative value of the traps or even the value of del phi f, the qualitative nature of variation of threshold voltage with temperature does not vary. So, if you look at the right hand side diagram here, we are plotting Vt, the threshold voltage, with respect to temperature, taking into consideration two things. The green one is basically del phi f equals to 0, and the red one is del phi f is included, right? And obviously, if you include del phi f, there will be a fall in the value of your Vt. We are again assuming that there is an incomplete ionization taking place, and therefore you see the red line actually is below the green line for all practical purposes, because you have included this. So there is a negative sign associated with it, and therefore the relative threshold voltage is always smaller. Interestingly, and this point is very important, you should note down, though I can show it to you here. Just concentrate at this edge where you are somewhere around 4.2 Kelvin or 5 Kelvin. There not only you have full incomplete ionization coming into picture, but you also have freeze outs. Freeze out will ensure that the red line, which is where del phi was included, will be still lower as compared to the green one where you have not considered. So basically, if you carry forward your classical picture of threshold voltage, you actually overestimate the threshold voltage at cryogenics. At cryogenics, the threshold voltage is much lower as compared to the previous one. And as you can see, both the curves are basically parallel to each other, which primarily means that qualitatively there is no change in their pathway. As I discussed with you, therefore, we have been able to predict by this discussion the threshold voltage variation with varying temperature, taking into consideration freeze out as well as incomplete ionization. Now, let us look at the impact of band gap widening on threshold voltage. We have seen it, and the left hand side is the graph which shows it. So, if you see, this is Eg by 2, right? This is the band gap which you see. Now, there are two curves here, the green one and a dotted red curve, right? The green one is assuming that it is a fixed band gap energy. Let us suppose for silicon 1.12 electron volt is there, and this is fixed. So, as you reduce your temperature, the threshold voltage goes on rising, as we know, as we have seen in our previous slide as well. However, when you take the Varshini model and there is a band gap change, you see that the difference between the green and the dotted red becomes larger at lower temperature, right? And that is primarily because of the band gap widening and its influence on the threshold voltage of the device. So, the band gap widens, and therefore it makes my threshold voltage relatively go higher with respect to fixed band gap criteria. Here we have taken the metal work function as 4.1, oxide capacitance per unit area is 22 millifarad per meter square. Chi is the work function, electron affinity, which is 4.05 electron volt, and we have taken Na in one case to be 10 to the power 17, in another case this is 10 to the power 18 Na and this is 10 to the power 17. Obviously, 10 to the power 17 Na will have a lower threshold voltage as compared to 10 to the power 18. So, you see what important things play a role in threshold voltage determination is, of course, the doping concentration, but that is known even at 300 Kelvin. If you are working with cryogenics, low temperature freeze out reduces the threshold voltage drastically. Band gap widening takes place, and that influences your threshold voltage. So, these are the few device level changes which you expect to see the threshold voltage change. Now, so the first one was basically was wide gap widening. This is now a figure showing you how the interface trap charges influence the threshold voltage. Now, and it has been seen that when you make your du large, right, and this is quite interesting. If you make your du large, as I am varying threshold voltage with respect to temperature, and if you look at these three curves, this is with increasing du. Du means basically the uniform trap charges density, and as you make it from 10 to the power 10 to 10 to the power 12, even at low temperature, there is a substantial change of 50 millivolt change is there, even with 2 order change in the value of your interface trap charges, right? Higher the value, higher is the threshold voltage. You all know the physical reasoning behind it. We have kept the acceptor ion concentration from 10 to the power 18, right? We are again assuming here that uniform trap charges are maintained, and therefore we have included del phi f, and because of that my uniform trap charge density happens to be this much, which we have already found out in the previous case. So, again, take away from this slide is that as you make your uniform density go larger and larger, you end up having a larger threshold voltage for all practical purposes. Now, come to the last part, and this is this Gaussian part, and this consists of the band gap widening part, and this is the right hand side is the Gaussian interface trap charges, and on the left hand side we have plotted threshold voltage with respect to temperature, and on the right hand side again threshold with temperature. And what we have seen in these two cases that the change n naught value, this right hand side has n naught value of 5 into 10 to the power 12, whereas the left hand side has an n naught value of 1 to 4, 1 to 5, 10 to the power 12, which we see. Similarly, if you look at W0, W0 is 20 millivolts here, and this is for various values of W0 of 20 and 100 millivolts. Now, if you see very carefully, at relatively higher temperature, if you look at the variation of threshold voltage here, at relatively higher temperature, all of these graphs become independent of the value of N0, right. So, if you are working at 100 Kelvin or let us say even 150 Kelvin, the threshold voltage will not vary too much with respect to N0, but this variation becomes more prominent when you actually reduce the temperature to sub 50 Kelvin temperature. At sub 50 Kelvin temperature, as you can see, there is a variation of the threshold voltage, right. There is a threshold voltage variation which is happening here, correct. So, as you make your N0 higher and higher, obviously your Vt goes on increasing, right, and difference becomes very large at low temperature. The same thing is true for the right hand side figure also for the Gaussian interface trap charges. Let me recapitulate what we did in this whole discussion, that we have taken this expression which you see in front of you now, and taken each one of them individually and see how does it vary with respect to temperature, right. And we were able to sort of find out which one is important as far as understanding is concerned. So, if you look at this model here, which is the Gaussian interface trap charges on the threshold voltage, if you look carefully, it actually has got this Eg by 2 already inbuilt into it, right. The Eg by 2 part is already inbuilt into the interface trap charge density concept here, correct. And that is the reason we say that these 4 elements, which is du, N0, del phi f and psi s, these are the 4 important sort of qualitative quantities which affect the value of the threshold voltage on a longer run, right, and that is what we have found out in this lecture. So, just to recapitulate what we learned in this lecture, we learned about 2 things. One is basically your threshold voltage variation with temperature and how the temperature gets influenced by interface trap charges, both Gaussian as well as constant. We also looked into Gaussian trap charges right, and we looked into the Gaussian trap charges, and we saw that it depends on the value of N0 and W0. We saw interface trap charges which are fixed in nature, and this is eliminated by D0, and we also saw later on that the variation of Vt threshold voltage with N0 at low temperature is quite substantial, right, but at high temperature this vanishes, this variation vanishes, right, and that is one of the important point. So, why important? This now we need to look into from the point of view of circuit analysis, that therefore, when we apply this threshold voltage model to our device in cryogenic, the threshold voltage rise up, and therefore, you need to do feedback mechanism in order to improve the value of the threshold voltage of a device, right. So, with this I think we will stop this lecture here, and till we meet next time, goodbye.